morning, dear student. In previous lecture, we will discuss what is photochemical reaction, what are the different laws of photochemistry, then what is the process, that is the process of deactivation. Then we study what is quantum yield, what are the causes of low quantum yield and high quantum yield. So in this lecture, we will discuss the reactions of electronically excited species. We know that atoms, molecules, electron absorb light radiation and goes into the higher energy state, that is excited state, and these excited state or these excited species shows different types of reaction. So they are classified into two types. So reactions of electronically excited species are classified into two types, that is, one is, if you consider, they are classified into two types. One is prompt reaction and second is delayed reaction. So the electronically excited species shows two type of reaction. One is prompt reaction and second is delayed reaction. The name itself indicate prompts means the lifetime of excited state is very small. So in this case the lifetime is large as compared to this species. Then they required very less time to convert into the products. So let us see one by one. So let us see first, that is prompt reaction, and then we will discuss the delayed reaction. So let us see this prompt reaction. So prompt reaction. So what are the characteristics of the prompt reactions? So we will discuss one by one. So the first characteristics of the prompt reaction, that is the excited state which is formed after absorption of light radiation immediately dissociate. So whatever the excited state which is obtained, so it have a very short period of time, so it will dissociate immediately after its formation. So first point is that electronically excited state dissociate immediately. So this is the first point. So whatever the excited state, electronically excited state which is formed, it dissociate immediately. So second, that is the time requirement for this prompt reaction is less than 10 picosecond. So time requirement is less than 10 picosecond, that is within 10 picosecond the reactions, that is the activated species or the excited species, is converted into the product. Then the lifetime, so in other words we can say that lifetime of excited state is very small. So these are the some characteristics of these prompt reactions, that is electronically excited state dissociate immediately after its formation. Within less than 10 picosecond the reactant, the activated species is converted into the product, and third one, the lifetime of excited state is very small. So let us see some example of this prompt reaction. So example, so the first example, that is CrCO6 in presence of H mu, that is light radiation, and in presence of solvents such as tetrahydrofuran, then it will convert into CO5 here, THF tetrahydrofuran plus 1 CO. So this is a decarbonylation reaction. So in this case the metal atom is attached to the 6 carbonyl. So while in this case the metal atom is attached to 5 carbonyl and 1 carbonyl is replaced by the solvent molecule, that is tetrahydrofuran. So this reaction is completed within less than 10 picosecond, and therefore it is considered as a prompt reaction, or this reaction is considered as a prompt reaction, that is decarbonylation reaction. Another example, that is a cobalt complex of ammonia, in which the cleavage of cobalt and chlorine ligand in presence of light. So we get here, so this cobalt, it is in +3 oxidation state. So we get here CO NH3 CONH3 it is in +2 plus Cl. So this is also a prompt reaction. So the wavelength which is required, lambda, which is equal to 395 nanometer for this reaction. So in presence of light, radiations, the cleavage of CO-Cl bond, that is metal atom and chlorine bond, and we get a product in which cobalt is in +2 oxidation state, because this ammonia is a neutral ligand. So this is also the example of prompt reaction. So for this second reaction, the quantum yield is equal to unity. So we know that quantum yield it is denoted by symbol phi, and for primary process the quantum yield is equal to unity. So for this reaction, if you decrease the wavelength, then the quantum yield for this reaction is equal to unity. Quantum yield is equal to unity. Then it is considered as a primary process, or this reaction follows the second law, that is Stark-Einstein's law. So one molecule absorbs one quantum of radiation, because the quantum yield is equal to unity by decreasing the wavelengths. So this is regarding to the prompt reactions, which is carried out in presence of light, but the lifetime of excited species is very small. So within less than 10 picosecond they are converted into the product, therefore they are considered as a prompt reaction. So let us see the delayed reaction. So what is delayed reaction? Just opposite to that of prompt reaction. Delayed reaction. So the first point regarding to the delayed reaction, that is the lifetime of excited species is greater than, is more, or we can say that the lifetime of excited species is more. So these excited species does not dissociate after its formation. So it will not convert easily into the product. So it will take a certain time to convert activated species into the product. So the excited state does not dissociate immediately. Does not dissociate immediately. And third one, so the time required, that is more than 10 picosecond is required to convert the activated species into the products. So these are the some characteristics of the delayed reaction. Let us see the example of this delayed reaction. So example is the complex, that is ruthenium complex, Ru bipyridyl third, it is in +2, because this ruthenium, because this bipyridyl is a neutral ligand, so ruthenium is +2. So after absorption of light, it will convert into ruthenium bipyridyl third, it is in +3. So this reaction it is not a simple digit transition reaction. This reaction is a charge transfer transition reaction. So in this case, the reactant in which ruthenium is in +2 oxidation state, while in the product it is in +3 oxidation states. So it undergo oxidation. So this ruthenium, it undergo oxidation reaction. So this is a charge transfer transition. This reaction is considered as a charge transfer transition, that is transformation of electron from metal to the ligand. So this is a MLCT, metal to ligand charge transfer transitions. So this is the example of MLCT, metal to ligand charge transfer transition. So transferring electron from metal atom to the ligand MLCT charge transfer transition. So oxidation state is increases by 1 unit. So this example is considered as a delayed reaction. So it required very much time to convert the activated species into the product. So this regarding to the type of the reaction shows by the electronically excited species. So in the next point, or the next important point regarding to the photochemical reactions, so the DD transitions and the charge transfer transitions are also occur in presence of these photochemical reactions. So DD transition and charge transfer transitions are also carried out by the absorption of light radiation. So what is this DD transition and what is this charge transfer transitions? So we will discuss what is charge transfer transition and DD transition, and they will see the example how the excitation, how the electronically excitation or electronic excitation is occur in presence of light radiation. So let us see the first one, that is DD transition. So students, you are very much familiar with this DD transition, that is, so for this DD transition, the transfer of electron from d orbital to the d orbital, that is the d orbital is get split in T2G and Eg, that is lower energy T2G orbital and higher energy Eg orbital in presence of ligand. So the splitting is occur and the transformation of electron from lower energy T2G orbital to the higher energy Eg orbital. Such a transition is considered as a DD transition. For DD transitions, we require ligands, because these ligands splits the d orbital into two orbital, that is one is lower energy T2G orbital and one is higher energy Eg orbital. So ligand is very important. So these ligands are of two types. If we consider the nature of the ligand or ligand field is very important. If the ligand is weak ligand, or the field of the ligand is weak and the field of the ligand is strong, so these ligands are classified into two types. One is weak field ligand and second is strong field ligand. In presence of weak field ligand, the delta octahedron is less than the pairing energy, while in strong field ligand the delta octahedron is greater than the pairing energy. So what is this delta octahedron and this pairing energy? So you should keep in mind the ligand, it have two types of ligand. One is weak field ligand and second is strong field ligand. So the field of a ligand is different according to the spectrochemical series. So some ligands are considered as weak field ligand, some ligand is considered as strong field ligand. In weak field ligand, the splitting, that is this delta octahedron is nothing but the splitting parameter, that is crystal field splitting parameter is less than the pairing energy, and in this case the splitting, that is the energy difference, so this is nothing but the energy difference between this T2G and Eg orbital after its splitting in presence of ligand. So delta octahedron is less as compared to the pairing energy. So in this case delta octahedron is more in case of strong field ligand. So how? So let us consider the gap, that is the nature of the ligand. If you consider a weak field ligand, so this d orbital is split into this T2G and Eg. So this is the gap is considered as delta octahedron. The energy difference between these orbitals is considered as delta octahedron. So in this case delta octahedron is less than the pairing energy, while in strong field ligand delta octahedron is greater than the pairing energy. So we can write here, so it shows a large difference. This is your T2G and this is your EG. So there is a large difference. Delta octahedron is greater than pairing energy. So this is the energy difference. What is its pairing energy? So if we consider a weak field ligand, what is its pairing energy? The minimum energy is required to pair the electron. The minimum energy is required to pair the electron. So in this case, the ligand is weak field ligand. So pairing energy is very high. So if we consider a 3 electron is present in T2G orbital, and if next electron you have to add. So in this case, the ligand is weak field, and in this case, the delta octahedron is very small, but the pairing energy is very high. So due to the very high pairing energy, the electron does not pair. So due to high pairing energy, so for pairing of electron, we required very much energy. So in this case, so instead of pairing, the electron goes into the higher energy orbital, that is EG orbitals. So this is the meaning. So delta octahedron is very less than pairing energy, because pairing energy is very high. So the pairing energy is not achieved, and therefore the electron is not pair. The electron is not goes into the T2G orbital. Instead of, it will goes into the EG orbital, because we require lot of energy to pair the electron. But in this case, if you consider the strong field ligand, the delta octahedron is very large as compared to pairing energy. Again we consider a 3 electrons, 2 and 3, and if you add a next electron, then in this case delta octahedron is greater than the pairing energy. So pairing energy is less as compared to weak field ligand. So less energy is required to pair the electron, and therefore next electron is goes into this T2G orbit. So this is the difference between weak field ligand and strong field ligand. So in presence of weak field ligand, the complex which is formed is called as high spin complex. High spin complex. While in presence of strong field ligand, the complex which is formed is considered as low spin complex. Low spin complex. So this is the effect of ligand field. In presence of weak ligand field, delta octahedron is less than pairing energy. So pairing energy is very high. Therefore, the electron not pair, so it is goes into the higher energy orbital. So in this case, the pairing energy is less. Therefore, the electron acquire this pairing energy and it becomes pair, and it is goes into the T2G orbit. So these weak field ligands are high spin complex, and these strong field ligands are low spin complex. If we consider the transition, let us consider the rules, selection rule for these DD transitions. So selection rule for DD transition is delta S is equal to 0, then it is spin allowed. And if delta S is not equal to 0, then it is spin forbidden. So these DD transitions occur by absorption of light radiation. So we know the strong field ligand, weak field ligand, high spin complex, low spin complex. Then the selection rule, that is delta S is equal to 0, spin allowed transition, delta S is not equal to 0, spin forbidden transition. So let us see some examples of these DD transitions. That is the example of titanium trichloride. When it dissolves into water, it will form TiS2O6, and this titanium, it is in +3 oxidation state. So we know that titanium, the valence configuration is 4s2 3d2. Okay, so it is in +3 oxidation state. So it is in +3, so 4s0 3d1. So it have only one electron into the T2G orbitals. So it is in +3, so it contain only one electron in d orbital. So in presence of ligand, this titanium forms a complex, and the splitting of d orbital into two energy orbital, that is one is T2G and another is EG, and this electron, a single electron is present in the T2G orbital, and this electron goes into the Eg orbital by absorption of light radiation. When it absorbs light radiation, then it will goes into the Eg orbit, that is your Eg T2g. This electron goes into Eg orbitals. So if we consider the spin of the electron, in this case is 1/2, here also the spin is 1/2, so no change in spin. So if you consider the selection rule for this transition, that is the electron get excited, or the electron will be shift from T2g orbital to the Eg orbital after absorption of light radiation. So this is considered as a DD transition. So transformation of electron from T2g to Eg, it is considered as DD transition. In this case the spin of the electron is 1/2, in this case the spin of the electron is also 1/2. If you consider the selection rule for this transition, delta S, which is equal to, so in this case it is 1/2, the spin is 1/2, so minus, in this case after excitation the spin is also 1/2, so total is equal to 0, so that is delta S is equal to 0, and this transition is considered as an allowed transition. This is a spin allowed transition. So those transition in which delta S is equal to 0, or electron does not change its spin, after excitation. So in this case it is +1/2, in this case it is also +1/2 after goes into the Eg orbital, and therefore delta S is equal to 0, and this is a spin allowed transition. If you consider another example, of chromium or cobalt complex, that is COF6 3 minus, another is cobalt NH36 plus 3. So in this case cobalt, okay, 4s2 3d7 configuration, here also cobalt 4s2 3d7 configuration, but both the cases cobalt is in +3 oxidation state, so 4s0 3d5. So in this case this cobalt, it is also in +3, so 4s0 3d5. This is the configuration. So this cobalt is +3, this cobalt is +3, but you should keep in mind the ligand, that is these halides are weak field ligand, while this ammonia is considered as a strong field ligand. So if you keep in mind, that is the cobalt in +3 and nickel in +3, if it is present, that is cobalt, it is in +3 oxidation state, and nickel, it is in +3 oxidation state, if it is present, then ammonia, it is also act as a strong field ligand. So ammonia is also act as a strong field ligand. So in this case delta octahedron is very large and pairing energy is very small. So if we consider the electron distribution, that is T2g and Eg, so in this case it is a weak field ligand, so 1, 2, 3, next electron goes into the Eg orbital, 4 and 5. This is because the delta octahedron is very small and the pairing energy is very large. So due to high pairing energy, the electron does not pair, it is goes into the Eg orbital. But in this case, if you consider T2g and Eg, so in presence of, that is cobalt is in +3 oxidation state, cobalt nickel, if it is present in +3 oxidation state, so this ammonia, it is also act as a strong field ligand. So in presence of strong field ligand, the delta octahedron is greater than the pairing energy, so less energy is required to pair the electron, and therefore 1, 2, 3, next electron goes into this T2g orbital and this is T2g orbital. So both electrons get pair. So this is the difference between strong field ligand and weak field ligand. If you consider this complex, and if you by absorbing a light radiation, that is one quanta of radiation, if this electron get excited or this electron transfer into this Eg orbital, then what happen? The spin of the electron get changed. So in this case the spin of the electron get changed. So in this case the electron having plus of spin, after transition the electron spin get changed into minus 1/2, and therefore this transition is not allowed. So it is spin forbidden transition, because delta S is not equal to 0 in this case. While if you consider this reaction, or if you consider this complex, if this electron is transferred to the Eg orbital, its spin does not change, and delta S is equal to 0. So whatever the delta S, whatever the spin for ground state, the same spin for excited state. So the delta S is equal to 0 in this case. If you consider this electron, if this electron is transferred into this Eg orbital, its spin is minus half. Again after excitation the spin is also minus half. So in this case, if you consider this weak field ligand, after absorption of light radiation, this electron goes into the higher energy state or higher energy orbital, and the electron spin gets changed, and due to this the transition is spin forbidden transition. So it is not allowed transition. But in this case, any electron if transferred into the Eg orbital, the spin of the electron does not change, and it is spin allowed transition. Second is the delta S in this case is not equal to 0. Delta S is not equal to 0, while in this case delta S is equal to 0. So this is your spin allowed transition, this is your spin forbidden transition. So this is regarding to the DD transition. In next lecture we will discuss the charge transfer transition. What is charge transfer transition? What are the different types of charge transfer transitions? So these DD transition and charge transfer transition are also occur by the absorption of light radiation. Thank you.